In our next question, we're going to talk about how to really see past the answer as it's just given to you, or here's the trick to the problem, and to really break these problems down into a step-by-step methodical process. This question is titled, how do I make any use of this? And we should add in the word use here. Remember, the two key parts to dynamic programming are optimal substructure and overlapping subproblems. And this leads to two direct guidances. And here I can say tabular storage or cached storage, because they're actually two different formulations. The first part is we're looking for some optimal substructure. We're looking for something that can lead to a recursive formulation. We're looking for a way to take the big problem and to break it down into smaller problems. And along the way, we're looking for those smaller subproblems to overlap in some fashion. We're looking for, as we recursively formulate this, one of the subproblems that we've solving over here, we've already solved somewhere else. And that then leads to optimizations, a tabular optimization in the bottom-up approach, or a cached optimization, a memoized optimization in the top-down approach. Let me show you what that might look like for Bellman-Ford. Remember, in our Bellman-Ford, what we're trying to do is we're trying to figure out what is the shortest path from some source node to every other possible node in the graph, assuming that there's no negative cycles, but allowing for things like negative weights. And one of the ways we could start this is we could look at all of the possible simple paths, a simple path being a path where there is no cycle. And so here, we're looking at all the possible paths from A to some destination. And so you can see here are all the possible paths to C, here are all the possible paths to E, here are all the possible paths to D, here are all the possible paths to B. And what we could do, computing every single possible path, is we could run a cost function on them and we could optimize and find what the best is. But what you can think is all of these paths is a combinatoric problem. Because if we have a lot of branching in our graph, then we have to say, okay, take the left branch, take the right branch. And if it's not just a tree or a directed acyclic graph, if there's the case where we might have some cycles here or something of that nature, or we can move laterally even, then we may discover that at point A, we have to make all these choices. Then at the next point, we have to make a bunch of choices. And the next point, we have to make a bunch of choices. And it splays out. And we have this combinatoric expansion, which makes it prohibitive for us to actually give us what are all the possible paths that I can then run a cost function over. We need to have some smarter approach. And so what we're going to do is we're going to think through this problem a little bit differently. We're not going to implement a cost function and then try and optimize over those paths, because we know that's going to be way too inefficient as this graph grows, because we'll have that explosion of possibilities to look at, that combinatoric explosion. Instead, we're going to look for the optimal substructure. Here's how I'm going to formulate it. I think in my graph, there must be some path from A to D. If this thing is fully connected, there is going to be a path from A to D. I don't know what that path is, but I know that the path exists. And I can say that path might go through B, it might go through C, and my choice is to figure out which nodes does that path go through. I can say that the shortest possible path from A to D, if it transits through any other node, like a node X in the middle, then this shortest path must be the sum of the shortest path from A to that transit stop, and then from that transit stop to the end, from that layover to the next point, from A to X and then X to D. And I'll prove it to you. If this shortest path is not the consequence of these two shortest paths, if there was another better way to get from A to X, then I would have just taken it, and then I would get the new shortest path. So we know if we take that shortest path, if it already exists and we decompose it, we know each incremental leg is already itself independently optimal. This is what optimal substructure is. The overall best answer is consisting of the best possible answer at each particular point. But when we're talking about these kind of dynamic programming problems, we're often talking about what you might call decision problems. And we'll see that in the formulation, we're oftentimes reformulating these in terms of some decision that's made at each step. Just because we can say that the optimal substructure exists, and we can say that the optimal path from A to D consists of the optimal path from A to X and then X to D, and we can break it down like that, we don't necessarily know what nodes are in that path. We know that we have this equation. The optimal path from D to A is the best path from D to X and X to D, but we don't know which nodes we went through. And what we have to do is we have to go through all the choices that we have. Maybe the best path is from B to E to D. Maybe the best path is from D to B to E or to D. Maybe it's through E and then through F and through D. We don't know which of these are the case, but we know that once we've identified which the case is, maybe it happens to be this one, we know that each one of these individual links must themselves be optimal, must be the shortest possible path. We just don't know if we needed to make that detour or not, if that detour was worth making or not. And you can see in this particular case, that detour may be worth making because E might have a negative weight. That's why it's better than this. Well, this is not a greedy problem because we don't know at the point when we're deciding which fork to go down the road, we don't know whether there's going to be a later fork down the road, especially one with a negative path or negative weight, which might then make it better to go down that path. We don't know if there happens to be from A to the end some shortcut that we didn't discover just yet, and that if we go down some path, we might preclude ourselves from going down that shortcut. Imagine you get to B, and then there's a fast path from B to D. We're here, or to E here. We're here, at the point where we're at A, we don't really know, do we want to go down C and we go down B without having global information of what's coming next. So there's clearly optimal substructure, and it's clearly not greedy. We also know that there are overlapping subproblems, and I'll show you why. If we consider the best possible path from A to some destination, in this case F, and we think about what that best path would be in 0 steps, well, the best possible path is an infinite number of steps. If we think about it in 1 step, then we're trying to say, okay, there's A to something, to F, and we can update this and say, okay, it's whatever the previous solution was, plus you're taking into account that we're transiting through this node here. If we're saying within 2 steps, then we can say, oh, well, it's whatever we did up to here, plus the best path up to here. And you can see here is this is overlapping subproblems because the subproblem that we're composing this problem out of is really just the problem of the best path to A to X. And bear in mind, in this Bellman-Ford, we're looking for the path from every node to every other node. So we're not just looking for A to F, we're actually looking for A to B, A to C, A to D, A to E, and A to F. So it's very likely that when we were evaluating one of these layovers, we may have already evaluated it before as part of another problem we were solving. And the idea of Bellman-Ford is we start with an infinite assumption, an assumption of in 0 steps we can't get anywhere, so it's a cost of infinity. And then we go through 1 step at a time and say, well, if we transited through here, is that any better? If we transited through here and here, is that any better? If we transited through here, here, and here, is that any better? And that's what that relaxation step is. When we think about this Bellman-Ford, or when we think about these algorithms, we can think about these, or we can formulate these in either a top-down approach or a bottom-up approach. What we'll discover is because there are these overlapping subproblems, and because we don't want to recompute those overlapping subproblems, well, we can either memoize results, that's just add a cache decorator on top and call it a day, or we can build up from an inductive formulation. We can start with the kernel, the base case, and then build out. This is what you might call a tabularized approach. Let me show you an example of this. A canonical example of a dynamic programming problem is interval scheduling. There are 2 variations of this problem, unweighted and weighted. Interval scheduling means I have some jobs and I have some starting point and some stopping point. And I want to figure out what jobs, what non-overlapping jobs can I pick to get the most amount of work done. And here, we're going to look at first an unweighted interval scheduling problem. In an unweighted scheduling problem, then we're basically trying to see what's the most number of possible jobs I can pick. So you can see, I can't do A and B together. I can't do B and C together. I can't do C and D together. I can't do D and E together. I'm not going to do the combinatoric expansion of every possible way to pick 0 jobs, every possible way to pick 1 job, every possible way to pick 2 jobs, every possible way to pick all 5 jobs, and then reduce it down to the ones that are non-overlapping, and then run a cost function over that, because that'll be way too expensive. Instead, what I'm going to do is I'll employ a very simple formulation to figure out what the answer is. And eyeballing this, I kind of know what the answer is. Probably the most number of jobs I can pick would be I pick A, I pick D, and I pick E, and I ignore B and C. And that gives me 3 jobs that don't overlap. Here is my formulation for this problem. I'll start with a little bit of data. And in this sample data, I have all these jobs and the begin time and the end time for these jobs. And With a little bit of mechanics, I can basically sort these jobs from when they started and when they ended. So I can put these in sorted order, and I can just go through and I can say, okay, if I haven't seen any jobs yet, pick the first job. And then just pick the next job that doesn't overlap. And this formulation does in fact give me the optimal number of jobs. In this particular case, A, B, C, D, and F are the optimal jobs that I want to pick in order to schedule as many possible jobs that do not overlap. And if we look at this data, we can see no overlap, no overlap, no overlap, no overlap. We seem to have a working solution. Interval scheduling, if they are unweighted, if the jobs are unweighted, if it's just the total number of jobs, or as they say, you want to get the highest cardinality in the answer, well, it's actually a greedy algorithm. And you can see the greediness here. I never revisited a previous choice. But if I make this the weighted interval scheduling problem, where there is a value associated with these jobs, then we can begin to see something a little bit harder. Because if I sort these jobs from the earliest starting time to the latest starting time, and I'm just going to proceed through them one at a time, I can make bad choices. If I just pick, oh, I don't have any jobs, so I'll pick E. Well, E only has a value of 1. And once I hit B, I can't pick B because it overlaps with E. And I probably, because notice they end at the same time, I probably shouldn't have even picked E in the first place. I probably should have revisited that choice and picked B in the first place because it's worth a whole heck of a lot more. This is a dynamic programming problem. And I can solve it as a dynamic programming problem. And the way to solve it is to put together a little bit of a formulation around two things. One, I'm going to define this idea of a predecessor. And the predecessor will be, if I take all the jobs and I put them end to end from the ending time, sorted in the ending times. So in this order, where they're now sorted by the ending times. And as much as I hate to do it, if I reset my index, so I put a number on these, that range index always gives me pause here. What I can say is, if I sort this in this order, I can define that the predecessor job is the latest possible job that works with a particular job. So I could say the predecessor job for A here, for number 6, would be number 5. The predecessor job for number 5 would be G. That would be the latest possible job I can fit in. For G, it would not be F because F overlaps. It would be C here because C doesn't overlap. And here you can see the latest possible job would be, B or E, and I can put a little bit of sorting here on the value as well. What I can say is, for this problem, the optimal answer, considering n total jobs, can be constructed as follows. If I consider 0 jobs, then the optimal answer is no jobs or no jobs to pick from. At each step, I can say that the optimal number of jobs are either a choice, a decision. Do I choose that job and include it or not, or do I not choose that job? And it is this choice that then leads to the optimal substructure and leads to the simple formulation. In other words, what I can do is as follows. If I think about this in terms of a choice I can make, I can see the decomposition of the problem. At every step, I'm going to consider job n, using where that n is basically my range index. It's basically my iLock here. So I'll consider 6. I can choose 6 or I cannot choose job number 6. Then I'm going to decide whether I want to choose 5 or I cannot choose number 5. Then I want to see if I can choose 4 or not choose number 4, and so forth and so on. And in the case where I choose that job, then I know that precludes me from choosing other jobs. If it's the case where I don't choose that job, well, then I can decompose the problem to the problem ignoring that job. And so we can see that in the cases. If I select the job, then I can't use any of the jobs that would be overlapping. Therefore, the optimal solution must be all the jobs up to this predecessor that I've identified, up to the latest possible job that could fit. And my optimal answer is the value of the job that I chose plus whatever the optimum is for the next starting point that I can choose from, the next possible job I can choose. If I don't select that, then my optimum is just ignore it and move on. And in this case, because this is not a greedy algorithm like the unweighted interval scheduling, because it's a non-greedy algorithm, because I may have to revisit choices, the way I adjudicate this is I take both chances. I splay this out. I choose all the possibilities. In other words, I implement my optimization in the following. If I'm looking at job 0, then, there's nothing going on. There's no jobs left. That's my base case. Otherwise, I choose the best of the two choices. Either select the job and get its value and reduce what I can look at to whatever the jobs that are left that are possibly compatible with what I have or don't. And I can actually implement it in almost exactly those terms with a little bit of ugliness just to make my panda structure work. Here is my predecessor function. This just gives me the first possible job, the latest possible job that's compatible with the thing I just chose. Here is my optimization. Notice the formulation is exactly the formulation we just looked at. If there are no jobs left, you get a 0. Otherwise, you maximize over either you get the value of that job and then decompose the problem, or decompose the problem for one fewer job. And if you can see, if I start with this and I ask it, and I change my panda structure into a little bit nicer structure for this formulation. Here, this tuple, I can ask for, what's the previous job for job 0? Well, there's no previous job for job 0. What's the previous job for job 4? Well, that would be job 3. And I can actually ask it, what is the optimal solution? You can see it says the optimal solution is a total value of 47. Now, I'd have to go and reconstitute what jobs those are. But if we look at the answers, we can maybe kind of guess. Here, we're only looking at the first 5 here, but we can kind of guess which ones they are. Or we could do something like, heck, we could print out, which these maxes were if we wanted to. Reconstituting the answer is pretty easy. The problem is, at every step, just like in that Fibonacci, I'm taking 2 choices. And then every next step, I'm taking 2 choices. And every next step, I'm taking 2 choices. And that's splaying out. Operationally, this is going to be really, really slow. And so if I increase the total number of jobs I'm looking at, not from 10 up to, say, 1,000, I'm going to see it's going to take a long time for this to recurse. And I might even get a recursion error along the way. But because I've identified that there are overlapping subproblems here, I can then use my caching trick. I can cache these so I don't resolve the overlapping subproblems. And you can see it's not fast, but it's not terribly slow. For 10,000, or I think it was 1,000 jobs, for 1,000 jobs, I can solve this in a half a second. And obviously, some of the mechanics for this, I can optimize this further. There's a little bit of hokiness around how we do this in Python. I can't push this into the restricted computation domain. But what we're seeing here with and without this memoization is the difference between not ever being able to solve this in any reasonable amount of time to being actually able to solve this. And we can see that the memoization here was not the main idea. The main idea was figuring out how to decompose this into 2 possible choices and then expressing this as an optimization where you're maximizing over those choices. That is how dynamic programming should be thought of. And when we talk about the top-down approach here, we're going to solve it by looking at the biggest problem and then decompose into smaller problems, and memoize to avoid resolving previously solved problems. Another approach we could take is the bottom-up approach, where instead of formulating it that way, we build it up from the bottom up. We solve the smallest possible problem. What's the best possible job we can have for 0 jobs? What's the best possible job we can have for 1 job? And we build that table up. And the reason that we know we can do that is, for any recursive formulation, you can always decompose that into an iterative formulation, either basically by introducing an explicit data structure. If you're doing it top-down, then that explicit data structure is going to be something that's probably stack-like. If you're doing it bottom-up, it's going to be some table where you're filling in the pieces as you go. You solve a small problem, then you say, okay, incrementally introducing a little bit more data, solve that next problem, and so forth and so on. And so here you can see an iterative implementation. If we want to construct the schedule, it's not too hard. We just have to kind of pull that out there. Maybe we yield the data, and you can see here's what the schedule would actually be for this problem. That's how we should approach dynamic programming problems, by first looking for the optimal substructure, discovering what that optimization is and the choices, and then, once we've identified that, looking for overlapping subproblems and using the bottom-up or the top-down approach, either the memoization or the table building, in order to optimize the actual runtime, the actual execution of this splayed-out choice.